We now start module 4 of chapter 2, and now it is time to introduce a few very important concepts of linear algebra, namely linear independence and dependence of vectors in a vector space V. You will see that this will enable us to answer quite a few questions that we raised in the previous modules. So, let us start with linear independence and dependence of vectors in a vector space V. Let V be a vector space over a field F. Now, we introduce the concept of linear independence of vectors. Suppose that V1, V2, Vn is a finite non-empty set of vectors of V. Now, we say that it is linearly independent over the field F if A1, A2, An are scalars from the field F, and if the linear combination A1, V1 plus A2, V2 etc. up to An, Vn is the 0 vector, then the scalars A1, A2, An must be all 0. What does that mean? We have the trivial linear combination, that means the 0 dot V1 plus 0 dot V2 etc. up to 0 dot Vn is equal to the 0 vector, and this is always true. Therefore, the 0 vector is surely a linear combination of V1, V2, Vn, whatever these V1, V2, Vn are. This is always true in a vector space V. Linear independence of this set of vectors V1, V2, Vn ensures that the trivial linear combination which you see above is the only way you can express 0 in terms of V1, V2, Vn. This is precisely what we mean by linear independence of finitely many vectors in a vector space V. Now, we extend this definition for any non-empty set, not necessarily finite. Let S be a non-empty subset of the vector space V. We say that S is linearly independent over the field F if every finite subset of S is linearly independent. And you have seen in the previous slide what is meant by linear independence of finitely many vectors. Time to see some examples. The set E1, E2, En is a linearly independent subset of f to the power n for any field f. And what are these E1, E2, En? They are nothing but Ei is the vector where 1 occurs at the ith spot and 0 everywhere else. Why is it so that it is linearly independent? So, we have to prove that if A1, A2, An are from the field F, and if A1, E1 plus A2, E2 etc. up to An, En is the 0 vector, then A1, A2, An must be all 0. But what is A1, E1 plus A2, E2 and so on up to An, En? It is nothing but the n tuple A1, A2, etc. up to An, which is the 0 vector. That means A1 is equal to 0, A2 equal to 0 and so on, An is equal to 0. This proves that the set E1, E2, En is linearly independent over F. Now, the vector space of matrices. Just consider the set of all 2 cross 2 matrices with real entries. we know that it is a vector space over R, and if you look at this particular set consisting of 4 matrices, namely 1 0 0 0, then 0 1 0 0, 0 0 1 0 and 0 0 0 1, then this set is indeed linearly independent over the real field. Again, something very easy to verify. And of course, this set is spatial in some other sense as well, and that is this spans the vector space M2R. So, this is a spanning set which is also linearly independent. We will see that these are indeed the very special ones for a vector space V. So, a non-empty set S is said to be linearly dependent over F if it is not linearly independent over F. What does that mean? That means there are finitely many vectors V1, V2, Vn in V and scalars A1, A2, An in F, such that the linear combination A1, V1 etc. up to n Vn is equal to the 0 vector, but not all the scalars A1, A2, An are 0. That means there is at least one AI which is not 0. This is what linear dependence of a set is. Probably the simplest example would be just the singleton of the 0 vector, which is linearly dependent, because if you take any A from the field F, then A dot the 0 vector is the 0 vector. Therefore, we surely have a non-trivial linear combination which gives rise to the 0 vector. One more example where the vector space is R2 over the field of real numbers. If you look at the expression 1 dot 1 1 minus 1 dot 1 0 plus 1 dot 0 1 is equal to 0 0. So, you see a non-trivial linear combination giving rise to the 0 vector, and therefore, the set of vectors consisting of 1 1, 1 0 and 0 1 in R2 is linearly dependent over the real field. Let us learn this theorem now. Let S be a linearly independent subset of V, and let V be a vector which is outside S, that is V is in V minus S. Then the set S union singleton V is linearly dependent if and only if the vector V belongs to span of S. Proof: if S union singleton V is linearly dependent, then the set V comma V1 comma V2 etc. up to Vn is linearly dependent for some V1, V2, Vn subset of S. Since we know that S is a linearly independent subset of V, therefore, we do have a non-trivial linear combination of V, V1 and Vn giving rise to the 0 vector, which is AV plus a1 v1 etc. up to an vn is equal to the 0 vector, where a1, a2 etc. up to an are elements in the field F, and A must be non-zero. Why is that so? Because if A is 0, then we would have a1, v1 etc. up to an vn is equal to 0, but v1, v2, vn is a subset of S, and S is linearly independent. Therefore, it would force all the a1, a2 etc. up to an to be 0, and then a1, a2 and etc. up to an all are 0, which of course does not show linear dependence of the set V, V1 etc. up to Vn. Therefore, we must have that A, the scalar A must be non-zero. But F is a field. So, A being non-zero, we have A inverse in the field F, and therefore, if we push everything on the right hand side and keep just a v on the left hand side of that expression, and if we divide the whole thing by A, in other words, if we multiply the whole thing by A inverse, that shows that V belongs to span of S. So, we have proved that if S union singleton V is linearly dependent over F, then V has to belong to the span of S. Let us now prove the converse of this statement, that is, if we know that V belongs to the span of S, then S union singleton V is linearly dependent. If V belongs to span of S, then V is a linear combination of finitely many vectors from S, that is, V is equal to a1 v1 plus a2 v2 etc. up to an vn for some a1 a2 an in F. Therefore, a simple rearrangement shows that V minus a1 v1 minus a2 v2 etc. up to minus an vn must be the 0 vector. You can see that this is a non-trivial linear combination of vectors giving rise to the 0 vector of the vector space V. And why is it a non-trivial linear combination? Because the coefficient associated with the first vector V is 1. Therefore, the set S union singleton V is linearly dependent over the field F. We know what is a spanning set of a vector space. We also know what is meant by linear independence of a set of vectors in a vector space. Now, it is time to see them together, in the sense that suppose we have a spanning set which is linearly independent. Is it somewhat special? More importantly, what do we really mean by this adjective special? And if you remember, we have talked about a spanning set, and we were indeed looking for a spanning set which is smallest in the sense of set inclusion. Can that be seen in view of linear independence? This is the time when we answer all these questions and also understand them better. we now introduce what is called a basis of a vector space. A basis B for a vector space V is a linearly independent spanning subset of V. You will see why basis is so important. You will understand it well as we proceed. So, first the example, the set of vectors E1, E2, En is a basis for Fn, where Ei is nothing but the vector where 1 appears at the ith position and 0 everywhere else. You have already seen that this set E1, E2, En is indeed a spanning set for f to the power n, and also you have seen that this set is linearly independent. Combining these two, you have a basis for the vector space f to the power n, and this is called the canonical basis of f to the power n. The vector space Rnx, that is the vector space of all polynomials with real coefficients whose degree is at most n, and we have already seen that it is spanned by the set 1 x etc. up to x to the power n. What is important is that this set is also linearly independent. Why is that so? So, if we take the linear combination of 1 x and so on up to x to the power n, that would look like a0 into 1 plus a1 into x and so on up to an into x to the power n, where a0, a1 etc. up to an are in the real field R. And if this linear combination is equal to the 0 vector, that means the 0 polynomial, then it is a defining property of the polynomial that a polynomial is the 0 polynomial if and only if all the coefficients are 0. Therefore, we have that a0, a1 etc. up to an are all 0. This proves that the set 1 x, x square and so on up to x to the power n is linearly independent. Therefore, this is a linearly independent spanning set of the vector space Rnx. That means it is a basis. Now, we see the infinite dimensional example, that is the collection of all polynomials with real coefficients without any restriction on their degrees, which is of course a vector space over R, and this set 1 x, x square etc. x to the power n etc., the infinite set, is indeed a spanning set of this vector space. And just because of the similar reason, this is also linearly independent, and therefore, this is a basis for the vector space of polynomials over the real field. Let us understand the basis with the help of this theorem. Let B be the set V1, V2, Vn, which is a non-empty finite subset of V, then the following statements are equivalent. The first statement is that B is a basis of V, and the second statement is that every vector V in V can be written uniquely as V is equal to a1 V1 plus a2 V2 and so on up to an Vn for some a1 a2 an in F. So, what do we mean by saying that the following statements are equivalent? That means, if we assume that the first statement is true, then we should be able to prove the second statement, and conversely, if we assume that the second statement is true, then we should be able to prove the first statement. We now come to the proof of the theorem. We first prove that 1 implies 2. That means, if we assume that the first statement is true, then we should be able to prove that the second statement is also true. Every V in the vector space V can be written as V is equal to A1 V1 etc. up to An Vn for some A1 A2 An in F, and V1 V2 Vn are of course in B, and that is true because V is the span of B. We now have to show that this expression V is equal to A1 V1 etc. up to An Vn is unique. What does that mean? That means if you have one more linear combination using V1 V2 Vn given by B1 V1 etc. up to Bn Vn, and that also represents V, then the scalars should match. That means A1 should be equal to B1, A2 should be equal to B2, and so on, An should be equal to Bn. This would prove uniqueness of expression. So, let us rewrite V is equal to A1 V1 etc. up to An Vn is equal to B1 V1 etc. up to Bn Vn, and we rearrange, which gives rise to A1 minus B1 into V1 and so on up to An minus Bn into Vn, and that is equal to the 0 vector. But V1 V2 Vn is exactly the set B, and it is linearly independent. Therefore, these scalars A1 minus B1, A2 minus B2 etc. up to N minus Bn, they must all be 0, and therefore, A1 is equal to B1, A2 equal to B2 and so on, An is equal to Bn. This shows that V written as a linear combination of V1 V2 Vn is indeed unique. Now, we prove the converse, that means 2 implies 1, that is, if we assume that the second statement is true, then it proves that the first statement is also true. The second statement is that every vector V in the vector space capital V can be expressed as a linear combination of V1 V2 Vn and uniquely. Therefore, it is clear that V is indeed spanned by the set B. The only thing that we have to prove now is that the set B is linearly independent over the field F. What does that mean? That means if we have scalars A1, A2, An coming from the field F, and if the linear combination A1 V1 etc. up to An Vn gives you the 0 vector, then we should be able to prove that A1, A2 etc. up to An are all 0. But we know this trivial linear combination, that means 0 dot V1 etc. up to 0 dot Vn is equal to the 0 vector, and statement 2 says that such linear combinations are unique, and therefore, by the uniqueness of expression we get A1 must be equal to 0, A2 must be equal to 0 and An is equal to 0. Therefore, the set B is linearly independent, and therefore, the set B is a linearly independent spanning set, that is a basis of the vector space V. a contextual remark. In this theorem that we talked about just now, we can actually take B to be any non-empty subset of V, which has to form a, and then we can prove that uniqueness of expression and conversely. So, it is not important that we have to work with a finite set only. Now, we define finite dimensionality of a vector space. A vector space V is said to be finite dimensional over a field F if V has a finite spanning set. Examples: f to the power n, that is the collection of all n tuples with entries from the field F, Rnx, that is the collection of all polynomials with real coefficients whose degree is at most n, M and R, that is the collection of all m cross n real matrices, are surely some examples of finite dimensional vector spaces. Why? If you just recall, then f to the power n is spanned by E1, E2, En, the so called canonical basis. Rnx is spanned by 1 x, x square and so on x to the power n, and M and R is spanned by the matrix units, and each one of these is a finite set, and therefore, these vector spaces are indeed finite dimensional. But the vector space Rx, that is the collection of all polynomials with real coefficients without any restriction on degree, is of course a vector space over the real field, but it is not finite dimensional. That means, we cannot find a finite spanning set for this vector space. Why is that so? Well, it is easy to argue. Suppose that there is a finite spanning set, and let us call that set F1, F2 and so on Fn. So, what are these F1, F2, Fn's? They are polynomials with real coefficients. Now, since you have finitely many polynomials and each polynomial has a degree, assuming that none of them is the 0 polynomial, if we require that these F1, F2, Fn must span Rx, that is not quite possible, because any linear combination of these F1, F2, Fn's can have degree which is at most the maximum of the degrees of these F1, F2, Fn. Therefore, if we choose a polynomial f whose degree is bigger than the maximum of the degrees of F1, F2, Fn, then we cannot write it as a linear combination of these F1, F2, Fn, which shows that Rx cannot be a finite dimensional vector space over the real field. We are through with the fourth module of chapter 2. We have seen the definition of a basis of a vector space, which is a linearly independent spanning set. We have also learned the definition of finite dimensionality of a vector space. Now, we have two very important questions in mind. One is, if we have a non-trivial vector space V over a field F, can we prove that it has a basis? And the second question is, assuming that the vector space V is finite dimensional, is it true that any two bases of the vector space V, assuming that they exist, have the same number of elements? We will see in the next module that the answers are affirmative in both the cases, and this will enable us to define the concept of dimension of a vector space.